So let's take two one-port devices now, and let's connect them together. So we'll have the network on the left, the one-port device, we'll call microwave network number 1, and the one on the right we'll call microwave network number 2. More specifically, we're going to say the microwave network number 1 is the port there we're going to call the output port, and on number 2 the port is the input port. So we're connecting the output of microwave network 1 into the input of microwave network 2. Now, how to define the difference between the output and the input? And we do that by based on looking at the rate of energy flow across the interface between these two ports. So more specifically, we're going to look at the direction of energy flow. So if we go through and we look at the direction in which energy is flowing in this circuit, we find that energy is flowing out of one device and into the other. Then this device from which the energy is coming, we call that the source, and that's why we say its port is the output. It is the port that is outputting energy. And then the other source, where the energy is flowing into, we call that the load. And that's why the port is called the input port. The energy is flowing into that port. And so this is a very simple model. We've connected two devices together, two one-port devices, and we find that energy flows between them. And depending on the direction of that energy flow, we call one device, one network, the source, and it outputs energy into the load, the other device, into input into its port. So we can go through, well, the question is, what is this source? It could be a very complex circuit. What is this load? Again, it could be a very complex circuit. The only constraint that we're going to have at this point is that the energy is of the form of a sinusoidal function, that we have generated the energy such that all the voltages and currents are sinusoidal with respect to some frequency omega. So can we come up with a model, an equivalent circuit for these two ports? Let's first look at the network on the right, what we call the load. Energy is flowing into this device, so it is a passive device. It's not creating energy, it is absorbing energy. And again, we're going to assume that is linear time invariant if we're using sinusoidal currents and voltages here. And we know that the relationship, therefore, between the voltage at that port input, the input voltage, and the current into that device, those complex voltages and currents must be related by the eigenvalue of the single port device, the impedance of this value. And so here the model is very simple. We go through and determine the impedance of this single port device, and that becomes essentially the mathematical model. We model this blue box as if just inside the port there is sort of a lumped impedance. Now we have two names for this lumped impedance. On the one hand, we know from the model, we know from the definition of impedance, that it is the ratio of the input voltage to this one port device to the current voltage, input to current rather, of this one port device. And so we can call that the input impedance, and it is the input impedance of this one port device. Yet this one port device is also the load for the source on the left, and so it is likewise equal to the load impedance. And this causes some confusion in this class. We talk about the input impedance of a passive load, and that describes it, but if we connect a source to that load, that impedance now becomes the load impedance, the impedance connected to this load. So we use these two interchangeably, and you need to make sure that you understand what we mean and what we're talking about there. So the model is pretty simple. Again, we have a passive one-port device. We characterize it by its impedance. It is the input impedance of the one-port device, and therefore it is the load of the source that's connected to it. What about the one-port network on the left then? We said that is the source. Energy is coming out of that one-port device. Can we characterize it with its impedance? Well, not only its impedance. That is not sufficient to characterize a one-port device that is a source of energy. One thing about device that's a source of energy, and the way you can tell it's a source of energy is if you connect an open circuit to that device, connect nothing to it, or connect a short circuit to it. If it's a passive device, the voltage across that open circuit would be 0. Likewise, the current to the short circuit would be 0. But if that device is a source, it supplies energy, what we'll find is that the open circuit voltage will be non-zero. It'll be dependent on the energy source within the device itself. Likewise, the current through a short circuit will be non-zero. And these are the two fundamental measurements that we make on a one-port device that is a source of energy in order to characterize it. First, we measure the open circuit voltage. We know the open circuit current, of course, must be equal to 0 by definition of an open circuit. Likewise, we go through and we put a short circuit on our port, and we measure the current through it, the short circuit output. Notice the voltage of the output is equal to 0 by definition of the short circuit. This is, again, an issue for some students. Sometimes they'll calculate the open circuit voltage and decide that the open circuit current is something other than 0, or the short circuit current, but then decide the open circuit voltage is something other than 0. So make sure that you get that right. So these are the two values we need to find. Take a port, put an open circuit on it, find its open circuit voltage, then put a short circuit at its output and determine the short circuit current. When I say determine it, what do I mean? In a laboratory, we would literally measure these two values. If we have the schematic of what's inside the blue box, then we can do an analysis to find these two values, the open circuit voltage and the short circuit current. So what do we do with those two results once we get them? We have two choices with respect to the equivalent circuit, or the circuit model, for a one-port device that is a source of energy. We can either use the Thevenin's equivalent, or we can use the Norton's equivalent, and each are determined from the open circuit voltage and the short circuit current. For the Thevenin's equivalent, the open circuit voltage is used to determine the voltage source, the equivalent source VG. It's simply an equality. The series source impedance, we'll call ZG here, is simply the ratio of the open circuit voltage to the short circuit current. So you can see the open circuit voltage in short circuit current is used to determine the two parameters of the Thevenin's equivalent circuit. For Norton's, it's kind of the same thing, only reverse. We take the short circuit current and use that to determine directly the source current. And then in parallel, we have a source impedance, which once again, just like Thevenin's, is the ratio of the open circuit voltage to the short circuit current. So these are two ways of describing the same thing. The device equations that result for the Thevenin's is this, and for the Norton's is this. And the key thing to point out here is that the output voltage is not equal to the source voltage, because we have a voltage drop across the source impedance due to the output current. Likewise, here for the Norton's, we find the output current is not equal to the source current, because some of that current likewise goes through ZG, the output impedance. And so make sure that you understand these equations, how they relate to the output current and voltage. And again, they are equivalent. We can use either one to describe these single-port devices. Notice if VG is equal to 0, then this becomes your short circuit, and this is described simply as an impedance. Well, VG is equal to 0, we have a passive device, and so we're back to the same characteristic we had for the source, or the network on the right, the load. It's simply a passive source device that absorbs energy. Same thing for the Norton's. If IG is equal to 0, well, that's an open circuit, and once again we simply have a single port device which is characterized by its impedance. And so we can see a passive device is just a special case of the Thevenin's and Norton's, special case when either VG is equal to 0, making this a short circuit, or IG is equal to 0, making this an open circuit. So this all seems very basic, yet this is a very important concept, a little bit of a trick that we'll do over and over again in this class that we do in microwave engineering. we'll take a very large system. This could be a receiver, transmitter, whatever. Very large, complicated system. And we're going to go through and look at one port. We're going to slice through and look at one port and determine the complex voltage and current here. Everything to the left of this port, we're going to lump into one blue box, which we call the source, and everything to the right, we're going to lump into one blue box, which we call the load. Energy is flowing from the source to the load. So we go through and pick a point in our circuit, energy flows across it, we're going to replace everything. Could be fantastically complex, this circuit, yet we're going to replace it with an equivalent source, and that equivalent source is simply a Thevenin's equivalent. We could use a Norton's, but we usually use a Thevenin's. Everything to the right, that's absorbent energy, we just replace it with its equivalent circuit. Well, that simply is an impedance, ZL. And this becomes then a replacement of a fantastically complex and sophisticated electrical engineering system, and we replace it with an equivalent circuit here. With respect to the current and voltage here at this port, we can determine everything about it just as simply with this than we can with this. And so we use this equivalent circuit to analyze voltage, current, the rate at which energy is flowing across power. We find everything, do the analysis for this particular circuit. And again, this seems simple, but the idea of an equivalent voltage, an output impedance, and an input impedance, ZL, those things are fundamental to understanding the rate of energy flow. And ultimately, in radio engineering, we're going to be very concerned with trying to maximize the rate of which energy comes out of this source and goes into this load. So something very simple reduces this. And again, students sometimes get a little frustrated. They're like, well, this is trivial. This isn't important. How could this be useful to us? This circuit that looks like something we might have seen our freshman year. Yet, again, these are equivalent circuits to these complex blue boxes. Because of that, I have these gray boxes here, and these gray boxes I call the ghost of circuits past. All right, we have a very complex circuit in the blue box, in which we could replace simply by its impedance. This is a representation, a model for what is physically true inside this gray box, yet we don't need to know anymore what's inside the gray box. The same thing here. This gray box is the ghost of circuits past, what used to be the source, and it is the source, but we can replace it in our analysis with the Thevenin's equivalent without any loss of knowledge. If all we're trying to find is what's going on outside of these two blue boxes in this region, we can replace them with their equivalent circuits, very simple devices, and get the correct answers. Harken back then to your freshman year when you had such a simple circuit, a voltage source with two lumped impedances in series, and we want to find the voltage across the second impedance and the current through both impedances there. We can use voltage division and Ohm's law and define then both the voltage and current. Once we find that voltage and current, again, these are complex values, we can go through and determine, and this is the most important thing to us with respect to radio engineer, the rate at which energy is flowing across that interface, the rate at which energy is flowing from the source to the load. And of course, rate of energy we call power. And how do we determine that power? If you go back to your freshman year, you almost certainly had a course where you went through and converted the complex representation of voltage and current into the time average rate of energy flow. How many joules per second are crossing across that interface? And that result was a result of 1/2 the real part of complex voltage V times the complex conjugate of current I. This is a very important result. Sometimes students kind of mess this up because I think it's been too long since they've seen it, and when they saw it the first time, they weren't quite clear what a complex voltage and current is. We can go through and take the time harmonic representation of voltage and current, the sinusoidal representation, and we can show that this result is true. We can take the time, the real value of time for both the sinusoidal voltage and current. We can multiply them together and then integrate over one cycle to find the average rate of power flow. And when we do that, we find that it's the same value we would get if we use the complex representation of voltage and current for those sinusoids and directly determine this. And this is something that happens over and over again. We know the complex voltage current represents the magnitude and relative phase of the oscillations, and we can determine things like power flow in terms of these real value voltages and currents with respect to time. And when we do so, we find we can directly determine that from their complex representation. We don't need to take the complex voltage and current and convert it back into real values of voltage and current with respect to time and determine power. We can directly determine power from the complex representations. And this is this result. Now, be careful here. There's lots of places where students mess up in this. First of all, we're taking the product of the complex voltage times the complex conjugate of the current. Oftentimes students don't take the complex conjugate of the current. They simply take voltage times current. Once you find the complex voltage times the complex conjugate of current, you get a complex number. Power is a real value. It is physical flow of joules per second, and therefore to determine the result cannot be a complex number. It turns out to determine the power then that is flowing into that load, the power absorbed by that load, we take the real part of the product of the complex voltage and the complex conjugate of the current. All right, so take the current, take the complex conjugate, multiply it by the complex voltage, you get a complex number. Take the real part. And this is where sometimes students have a difficulty. Go back and look at that procedure of taking the complex conjugate of the denominator and multiplying by 1, as such the denominator becomes a real value, so you can extract the real part. It's not a trivial operation to try to determine the real part of a complex number in many cases. The final step is divide by 2. Oftentimes students leave off the divide by 2. Why is that? Well, we go back to DC. From a power standpoint in DC, of course, it's simply DC voltage times DC current. There are no complex values associated with that. And since it's not changing sinusoidally, you don't have to divide by half. There's no time average power. And so I get a lot of times the power is equal to V times I, and multiply a complex voltage times a complex current, and that's the answer. That's wrong in for many ways. Again, you get a complex number, it has to be real, it has to be time average divided by 2. Make sure you take the complex conjugate. Lots of mistakes that happen here. Make sure you understand, we're not talking DC. This is where we get back to the point where the voltage may be 3 and the current may be -1. And so students say, well, gee, I can just multiply those two things together and get the power. Remember, voltage 3, it means 3 times e to the j0, -1 means 1 times e to the j pi, both complex numbers. Each has a complex conjugate. Multiply them together, take the real part. This is not a DC analysis. Now that we hopefully understand how to calculate the rate of energy flow across some plane, let's apply this to our equivalent circuit. So we've gone through and replaced a very sophisticated, complex electrical engineering circuit on the left that is supplying energy with its Thevenin's equivalent. Likewise, replaced a very complicated and sophisticated electrical engineering system on the right that is absorbing energy with its input impedance, now becoming the load impedance of this source. And all of a sudden, our very complicated and sophisticated electrical engineering system becomes very simple. It becomes very simple because all we're interested in now is what is the voltage right here and what is the current right here, the complex representations. Once we find that, we can determine the rate at which energy is flowing from left to right. How many joules per second are crossing that interface? Well, we do the analysis here, and again, this voltage can be determined from voltage division very simply, and this current can be determined from Ohm's law, Vg divided by the sum of these two impedances. We have to be very careful to take the complex conjugate of that resulting current, so we're taking the complex conjugate of Vg and likewise the complex conjugate of the impedances, and when we do the current, the result, happily for us, is that we get a magnitude squared. Remember, complex number C times the complex conjugate of that complex number is equal to the magnitude squared of that complex number. And that's why we get magnitude squares here for Vg, because we took that complex conjugate. If we hadn't taken the complex conjugate in the current, we just end up with some ugly complex number. We get Vg squared. Again, Vg squared is a complex number. The magnitude of Vg squared is a real value. And I get very grumpy when I grade things, and when you tell me that the that the magnitude squared of Vg is Vg squared. No, it's not. Remember, a complex number has both a magnitude and a phase. The power is related to the square of the magnitude. It's unrelated to the phase. So this is our result for we get for the power absorbed. This is the rate at which energy is passing across this interface. Notice here I use the units of joules per second. I don't like the units watts when it comes to power. I don't like the units any kind of a name for a rate. I don't like coulombs. It's I don't like amperes, for example. It is coulombs per second. I don't like watts. It's joules per second. When we convert a rate into, give it some name, I think it loses its physical meaning, and likewise it sort of gives to the student this idea that these are countable. That I got so many watts. I got three watts in my desk drawer and 2 watts in my pocket, and if I put them together, now I have 5 watts, as if I had. We're talking about dollar bills or pieces of candy. Watts are not countable. They're rate of energy flow, joules per second, and so I tend to use that units. Sometimes I'll refer to as watts or milliwatts, but oftentimes I'll talk about joules per second or millijoules per second, a rate of energy flow. So we look at this, and we keep in mind here, going back to calculating this, that the real part of ZL is the real part of the R plus JXL. And again, this is simply the real part of the impedance, which is RL. So the real part of the load impedance is simply equal to RL. Again, that's not necessarily a resistor. You look into the circuit, there isn't any resistor with RL. It just happens to be the real part at this frequency. So we went through and we determined the rate at which energy is flowing across that interface, the plane where the source is attached to the load. Now we're going to take that power, that rate of energy flow, and we're actually going to assign it to 2 different physical values. And we use conservation of energy to do this. If we have at this interface energy flowing at a rate of 10 millijoules per second, by conservation of energy, that means, in fact, energy is flowing out of our source at a rate of 10 millijoules per second. The rate at which energy is flowing out of our source we call the delivered power. The source is delivering power at a rate of 10 millijoules per second, or whatever that delivered power is. Likewise, on the right side, we have a situation where 10 millijoules per second, therefore, is going into the load. We say the load is absorbing that energy. It's absorbing energy at a rate of 10 millijoules per second. That is the absorbed power. In this case, of course, the delivered power is equal to the absorbed power. The rate at which energy is coming out of the source must be equal to the rate at which energy is going into the load by conservation of energy. By conservation of energy, we say the power delivered by the source is that absorbed by the load, and that can be determined by the rate of energy passing across this interface. Now this seems simple, and making this complicated. There's just power here. Why do we have to give it 2 different names? Well, later on what we're going to do is we're going to insert something between the source and the load. We're going to put a 2-port device, for example. And what we'll find in that case is there's some power coming out of the source, a rate of energy flow out of the source, and there's a rate of energy flow into the load. But because we have a 2-port device, something in the middle, the 2 powers will not be equal to each other. Conservation of energy will no longer hold. How could that be true? Well, we'll find because that 2-port device is altering the rate of energy flow. It's either increasing it or it's decreasing it. And so we want to introduce the concept of a delivered power, the rate at which energy is coming out of a source, and an absorbed power, the rate at which energy is coming into a load at this point. And yes, in this trivial case, they are exactly equal to each other. But in a more complex case where we slice this in 2 and drop a 2-port device between it, we'll find those 2 values are very different and have a different number than what we calculated on the previous slide.